Hello students, how are you? So let us start today a new chapter, chemical bonding and molecular structure. Okay, so today we'll talk about the Kossel-Lewis approach basically, and we'll see some application of the Kossel-Lewis. There is one formal charge theory that is based upon Kossel-Lewis. So basically, today we'll see upon this. Okay, and look at the various aspects of this. In the coming lecture, we will see Vesper theory, valence bond theory, and molecular orbital theory. Right. So what is first of all chemical bond? Okay, so first idea that we can we give it is something that is holding two things together that is called as bond. Okay, that's the basic definition of bond. Now, if that holding force is a bond, say chemically related, then we get it as chemical bond. So we have many bonds in our life also. So similar to that, if there is a bond between the atoms, then we call it as a chemical bond. Okay. Now formation of compound take place due to the different combination. Basically, it is saying that due to this different forces and all, we get different types of atoms. So you can think of it and just fantasize it that all the thing that you are seeing around is made up of electron and proton only. See, it is very simple to think it in this way that all of these things that are seeing here and there of varied colors and all, so they are all made up of electron, proton, and neutron. That's it, and you are here, you are with the beautiful world that you are seeing in front of yourself. Okay, so in this way you can think of how beautiful the creation is made. Okay, how beautiful the creation is done, that taking three simple things, okay, electron, proton, and neutron, we have built not we have built, but so God has built a very beautiful and colorful world. Okay, and in this, the main part that is contributing a lot to this beautiful world is the chemical bond. Okay, how the atoms are arranged, they are arranged with types of bond. They can be interaction, there are interactions, okay, they are also very important, but primarily there must be a chemical bond. So it was very important to know about how this chemical bonds are formed. For this, we have to study these theories. So first one, as I have said, that we will look at the Kossel-Lewis approach. So Lewis symbol. First of all, Lewis symbol. What is Lewis symbol? It is simple notation used to represent valence electron in an atom. Means we are only considering the valence electron, not the inner core electron. So why I'm saying these definitions and all, sometimes you are asked in the exams that okay, say or you can be asked that which of these are the correct statements, right? Which of these are the correct statements? In that case, you can be asked that okay, what is in Lewis symbol, the only the valence electrons are counted or not. So this in this way, question can be framed. So for now, this may seem native to you, but when it comes in your examination, it becomes a headache. So they next is the show the number of valence electron by dots around the chemical symbol. Suppose we have chlorine, they have seven valence electrons, so we will just put seven dots around the chlorine, and in that way we symbolize with the help of Lewis symbol. Now the number of dots indicate the common or group valence. Next is octet rule. Okay, so these two things are very important to move to this approach of chemical bonding that is gained by Kossel and Lewis. The second thing is octet rule. So octet rules, what does the octet rule say? It says that atom or an element should have 8 electrons in its valence shell. Then and then only that compound is stable. Okay, but this thing is busted many times, but still it was a good start. Okay, because most of the element or main group element, if we talk about, most of them have 8 electrons at the stable configuration, except hydrogen. Okay, but later on now, see, hypovalency and hypervalency are a thing there, but still, keeping that exception aside, it is a very good approximation without any knowledge of the insight that is going on. Now, how do this octet rule is satisfied? So we need 8 electrons, but element doesn't have this 8 electron. They can have 6, they can have 5, they can have 4, 3, 2, 1. It can vary from 1 to 7 also. So to say gain that electronic configuration, what do we do? First of all, we can transfer the valence electron, okay, either by gaining or losing. So first is transfer, means complete transfer. Not like transfer is going on that you are giving half of the share, okay. That is a complete transfer of electron. But this is the one way. The second way is called sharing valence electron. Okay, we can share the electron. Means that same electron, the one electron that is present, that is shared by the two electrons, and not half. It is fully shared. That this one belongs to this also, and this one belongs to this also. Okay, this may sound very abstract to you. That how can one electron not be distributed half, but one to both of them? So you are counting one electron as two, but this is the way it works. Okay, so I can't do anything for it. But that single electron will act as one electron for one element, and for the other element also between two, which is it is shared. In some cases, you will also see that a single electron is shared between three centers. So this is a very abstract thing to notice. That is called three center two electron bond. Means two electrons are shared between three centers. That is a different thing. But still, here is your thing that okay, you have one electron. Okay, that is not distributed half and half. It is distributed fully on both sides. Okay. Now, in 1919, Langmuir defined Lewis theory and introduced the concept of covalent bond. So here we have the Lewis theory of say element representation. Okay, now Langmuir what he did? He added the covalent bond theory to this Lewis theory. Okay, basically he used the Lewis theory to explain the nature of covalent bond. So when according to Lewis Langmuir theory, he said this according to this theory, a bond is formed when the electron is shared between two atoms. Okay, so when an electron pair is shared between two atoms, a chemical bond can be formed. So this is the minimum criteria. So this sharing of electron allows both atoms to achieve a stable configuration, typically the same as the nearest noble gas. Okay, so you must have seen this thing also earlier that okay, oxygen has 6 electrons, it can gain 2 electrons and gain the noble gas configuration. Okay, so it can become stable, right? Okay. Moving on to an example, here an example of chlorine, Cl2. So it is a halogen, has 7 electrons. Each chlorine will have 7 electrons. Both will need one more electron. Okay, both will need one more electron. Now, what will happen when two chlorine atom comes together? They can share their unpaired electron to form a covalent bond. Okay, what they can do? They can share the unpaired electron to form the covalent bond. So they can share a pair of electrons. So both have atom in this way achieve the noble gas configuration. See, this is a Cl. Okay, this is a Cl. Both are Cl. Now what did they do? They shared one electron, and they both have completed their octet. So see, they have shared their same electron between these two, and they have completed it, right? So you can think it in this way. See, this one electron is belonging to this also and to this also. This one electron is belonging to this also and this also, right? And it is not going halfway, right? If you take it half, then it would be 1, 2, 3, 4, 5, 6, and then 7. Half means 1, 7 should be there, but it has 8 electrons. Means it is completely shared to this also. Similarly, it is completely shared to this and this also. So this is unique about this structure. Okay. Now you can think of in this way. Now you just let this counting go away. Now think of it in terms of stability, right? That stability is mainly coming from the electrostatic distribution. So electrostatic distribution should be better. So here what the electron is there, 2 electrons are there. So it is providing that electrostatic environment that can balance the whole atom. So that is the main thing. It is not the counting, it is the electrostatic balance and the wave functions. Okay, so you know that the wave function, we studied it a little bit about it. So okay, we don't go into wave function. Simply you can think of that electrostatic environment that this electron is providing. That is the main reason for the stability. Okay, now here the dots that are present here, that represent the valence electron of each atom. So they are just the valence electron and not the inner core electron. We have inner core electron in say our chlorine because it has 17 electrons. So 10 electrons are there in their inner core, but we don't consider them. We only consider the outermost valence electron. Clear? Okay. Now let us take one more example here. So here we have water. Okay. Water, we have one oxygen and two hydrogens, right? One oxygen and two hydrogens are there in water. We know it very clearly. Now, if I talk about the number of valence electron of oxygen, it is 8. Sorry, it is 6. Okay, it is 6. Now, out of 6, the oxygen donates 2 of its electron in pairing, or you can say sharing, not pairing, in sharing. So one electron is shared to one of the hydrogen, and the other electron is shared to one of the hydrogen. And this is the overall Lewis dot structure of H2O. Okay, but the thing here to notice that all of the atoms that we're talking about, they are obtaining octet. Octet with 8, so it is basically derived from 8 only, octet. But your hydrogen is not getting an octet; it is getting a duplet. 2 electrons are there. Okay, it has 2 electrons, so basically it is duplet. Clear? Because what may be the reason behind it? Because 2 electrons is also a noble gas configuration if it has only one shell. Okay, if it has only one shell. So you can take the example of helium. It is only one electron, sorry, 2 electron, and it is still a noble gas and a stable one, right? So hydrogen is attaining a noble gas configuration that is close to helium rather than the other one that is attaining of 8. Okay, so it is not attaining the 8 rule, it is attaining the helium rule, that is duplet rule. Clear? Now let us take one more example. So we have an example of CO2 here. So carbon dioxide. So oxygen has again 8 electrons. You can see here that the 2 electrons of oxygen is involved in bonding. Okay. Similarly, if I talk about carbon, okay, if I talk about carbon, so carbon has 4 electrons, right? It has 4 electrons, so it will just donate its all of its electron to sharing. You can see count here. So this is an electron of carbon, this is an electron of carbon, this is an electron of carbon, this is an electron of carbon. Now they have shared it all. What is the total number of electron in carbon? You could take this, so you can think of it as a Venn diagram. Okay. So whatever falls inside this circle is the part of carbon. So 1, 2, 3, 4, 5, 6, 7, 8 electrons are there. Similarly, if I talk about oxygen, if you take this circle, so 1, 2, 3, 4, 5, 6, 7, 8. And for oxygen also 1, 2, 3, 4, 5, 6, 7. Clear? Is this clear to you? Okay. So in this way, they are sharing this electron. Now, whatever electrons are left out, what is the meaning of left out? So if you go back to the Venn diagram, so the one which is shared, which is in the union part. Okay, so if you do the intersection of this two circles, suppose if you are doing the intersection of this and this, then you will find these 4 electrons are in there in the intersection. Similarly, if you take this carbon and the right oxygen, then this intersection of these two again are taking 4 electrons, right? But in that case, if you see here, right, if you see here, these these 4 electrons of oxygen and these 4 electrons of oxygen are not falling under any intersection, right? So they are not shared. So once it gets into intersection of two circles, then we can call it as shared. Otherwise, they are non-shared, or we can think of it as a lone pair. Okay, so these all are lone pair of electrons. Clear? So it is basically coming from the word lonely. So it is lone pair because it is not getting shared between the two. Okay, clear? So this is the Lewis dot structure of carbon dioxide. Next, we have N2. So why I am giving you more and more examples? Because you can get an idea about it, right? Because in exam it is difficult to do so, to draw the Lewis dot structure. So you must be keen in drawing at least this, because this is also taught in the 10th class, right? So if we talk about nitrogen, so nitrogen has 5 electrons, it needs 3 more, it will need 3 more. So it will give its 3 electron and take also 3 electron simultaneously. So it is doing it here. So you can see that intersection of these two circles is getting 6 electrons, means 3 bond pairs. And 4 electrons are outside the intersection, and those are present as lone pair on both of this nitrogen equally. Now, here is one more thing that is called as bond order. Okay, we'll talk about it more, but now I'm just introducing it to you that it is the number, basically the number of bonds that are formed. So if you count it simply, for a nitrogen molecule, it is 3. Okay. Similarly, for the CO2, if you talk about between C and O, then bond order is 2. Here, bond order is 1, 1 in both sides. Okay, think of it in this way for different atoms. Clear? So this is the overall nitrogen. You can count the electrons also 1, 2, 3, 4, 5, 6, 7, 8. Okay. Here also 1, 2, 3, 4, 5, 6, 7. Okay, they have a triple bond, so bond order is 3. Now we will this Lewis dot representation of simple molecules. So we know that we have seen also that many of the molecules can be represented with the help of this Lewis dot structure, and they are very useful also. We will now later on see that this same Lewis diagram is kind of used when we are defining the structure, means that is remaining intact, that electron distribution is remaining intact, only the Vesper what it does, it just defines the spatial arrangement of the atom. Okay, that is also very important part. But still, the electronic distribution is kind of explained with the help of Lewis dot structure. Some of the exceptions are there, of course. We'll talk about the exceptions also. But before moving to that, let us see some simple steps in which you can draw, or in which you can from which you can write the Lewis dot structure. Okay, so we'll take the example of methane here. So how you will do it? So first of all, decide the central atom. So the one which is present in less amount, it is generally the central atom. Okay. So we will take that generalization. So we will put carbon between and put 4 hydrogens in a circle. Now, let us do it. So first of all, write the valence electron. Okay, one by one, just write the valence electron. If you are facing difficulty in differentiating between the dots, then you can use crosses also. Okay, you can use crosses also in for different. Suppose you're drawing it for methane, right? So you can use to represent dots for electron of carbon and cross for electrons of hydrogen. So that will help you to differentiate. Okay, that will help you to differentiate. Now simply just draw that circle. That would include. So if you're talking about CH4, so what will CH4 do? So each of the hydrogen will take 1 electron of carbon, and 1 electron from carbon will also be donated. So in one intersection of carbon and hydrogen, there will be 2 electrons. So there are 4 hydrogens, so 4 intersections will be there. Okay, there will be 4 intersections, and in each of these intersections, 2 electrons will be there, right? So in this way, the carbon will get 8 electrons, 4 into 2, and the hydrogen is getting its 2 electrons. So in this way, the octet of the methane is complete. Now, if I talk about the anions, so it means that we have an extra electron. So other than the valence electron that we have drawn, we will draw an extra electron also. Similarly, if you are talking about the cation, then we will remove 1 electron. So we will take the example of CO3 2- to explain it. So to complete the octet of CO3 2-, what do we need? First of all, 8 electrons for each. So carbon has 4 electrons. Okay, so it will donate 2 electrons to 1 oxygen. Now 3 oxygens are there. So 2 electrons to 1 oxygen, and remaining 2 electrons are distributed 1 to each of the oxygen. But now, if you just see here, the oxygen has got 1 electron from carbon also. Means the remaining 2 carbon oxygens have got only 1 electron, but they need 1 more. So for that, we need to complete the octet. So we put an extra electron both of these oxygens, and that creates 2 negative charge. Okay, so this is the CO3 2- for you here. This is the example of anion. Now let us take a cation NH4+. Now what when we'll take NH4+, so nitrogen will make 4 bonds here. Okay, it will make 4 bonds here. So for that reason, because it can make 3 bonds only. So for what is nitrogen doing? It is removing 1 of its electron. Why it is removing 1 of its electron? Because if you see in each of these cases, to go back, then all the electrons are present in pair. Or okay, so you can see pair. Okay, lone pair are present in always pair, or if they are donated also, there is still a pair. See, 1 pair, 2 pair, 3 pair. But when we are taking the example of NH4+, So it has donated its four electron, and now nitrogen has how many electrons in total? Say it has 5 electrons. Now four of it are donated, so one will be remain as a lone pair, and that is not observed. Okay, that is not observed. So that electron is removed, and also the octet is disturbed, because if it has 5 electrons and out of that five, four are shared, so it will also get 4 electrons back. Means the number of electrons that is shared, it is getting back that same number of electrons, means twice the number of 4, that is 4 into 2, 8 electrons in total for nitrogen, and plus that electron that has been left unpaired. Clear? Got it? So in this way, it is not possible for NH4 plus to say take that one electron or leave with that one electron. So here is a way to write, or here is an example to illustrate how we can write Lewis dot structure for different elements. So lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Neon has of course 8 electron. It has completed its octet. Okay. Now let us talk about some rules. Now we have seen that okay, the central atom is there and the side atom is there. Now sometimes the charge is there on the central atom in case of NH4 plus, and sometimes the charge is there on oxygen like the CO3 2 minus, or on the side atom. What is how we'll decide it? So the logic is very simple. Okay, logic is very simple. What we have to see simply is which is least electronegative and which is more electronegative. Most electronegative will bear the negative charge, and least electronegative will bear the positive charge. Okay, clear? Now let us take one more example, NF3. Okay, now fluorine needs one electron. Three fluorines are there. So three fluorines will need 3 electrons. And nitrogen also needs 3 electrons. So it will give first of all 3 electrons to fluorine, and it will get the twice of it back. So 3 to just 6, and 2 electrons are already there. So 5 were there, 3 were paired up. It gets back twice as that of 3, 6, and 2 that were remaining. 6 plus 2 is 8. Okay, clear? And one more thing, that the most electronegative elements are present on the surrounding atom. So they are present as a surrounding atom. So that is the thing I'm talking about. That is the reason this thing is kept here, because to illustrate that. Okay, nitrogen is least electronegative in this compound, and fluorine is the most electronegative. So we have placed fluorine as the surrounding atom and nitrogen as the central atom. Here also carbon is less electronegative, oxygen is more electronegative. So carbon is as the central atom and oxygen is as the surrounding atom. Now the basic requirement being that each bonded atom gets an octet of electrons. So this is the basic requirement, we know it. So here are some Lewis structure. Okay, so first of all we have hydrogen, so one electron shared duplet is formed. Oxygen, okay, we need a 2 electrons, so 2 bonds are there. It gets it 2 electrons. Now if I talk about ozone is something different. Okay, it is forming a dipolar ion because both positive and negative charge are present here. How did it been happen? So see, oxygen can make how many bonds? 2 bonds. Here it is making 3 bonds. So if it will do so, it will get more electrons than the required one. Okay, one extra electron than the required one. So what it does, it remove one electron, and that is the reason it is having a positive charge. Now this oxygen is making only one bond, and it needs to complete this octet. So it take one more electron from here, okay, which is being left out by oxygen, and therefore we are getting this type of structure. Clear? Similarly, NF3 is very simple to illustrate. CO3 2 minus I have told you. So here see, you can see that this 2 minus is on the braces. It is given on overall the compound. So if you just distribute it, then one will go on this oxygen, another will go on this oxygen. Next is HNO3. Okay, so nitrogen is there in the between. 4 bonds are again made. So it will have an extra electron. So that extra electron has been removed. And oxygen has only one bond with nitrogen. So it will have only 7 electrons. So it has got one more electron from the nitrogen that was donated by nitrogen. And it got the octet complete. So and this oxygen and hydrogen are already having the octet complete. So this is overall HNO3 structure. Now let us do some examples. So first of all, let us draw the Lewis dot structure of carbonyl, so CO molecule. Now the exception is given in the question only. Okay. Now first of all, we will count the total number of valence electron of carbon and oxygen. So carbon has 4, oxygen has 6. That will give you 10. Okay. So 2s2, 2p2, 2s2, 2p4. Now the skeletal structure of carbon dioxide is this CO. So we have not drawn the electrons, we have drawn just the skeletal structure. Now in this way it is formed. See here. Now here you can see that carbon has not completed its octet. It has only 4 electrons here. Okay, it has only 4 electrons here, and it is a exception to your octet rule. Clear? Draw a single bond between C and O, complete the octet of oxygen. The remaining 2 electrons are the lone pair of carbon. Okay. So this does not satisfy the octet rule. Okay, you can see it very clearly. It is not satisfying the octet rule. So what it will do now? Say, so what happens here is that, so we have carbon, it has 2 electrons that is being shared. Okay. Now what happens? Oxygen is having one more share pair of electron. What it does, one more electron pair on itself. So it gives that electron pair in sharing. So it is now also in sharing, right? Means both electrons which are shared between carbon and oxygen. So one of these pair belongs from the oxygen only and only. So this is the difference, because if oxygen would have made one more bond with carbon, then that would resulted in more electrons than 8. So for that reason, the shared pair of electron is coming from oxygen only. Clear? Now in this way, the octet rule is now completely verified. Okay, so this is the structure of CO. Okay, this is the structure of CO in which both of the octet, both are having their complete octet. Next is write the Lewis dot structure of nitrite ion. Okay, NO2 minus. So first of all, count the number of electrons. So it is 18 electron, right? It is having 18 electrons in total, including the charges or not. So we're counting the charge also. So 5 from oxygen, 5 from nitrogen, and 6 from oxygen. 2 oxygens are there, so 6 to the 8, 12, and 1 is the negative charge, so 1 is written here. So that will give you total of 18 electrons, right? Now the skeletal structure would look like this, because most electronegative atom is oxygen, so it is the surrounding atom, and the least electronegative is nitrogen, so it will be in the middle. Now in this way we can write it, the valence, including the valence electron 1 2 3 4 5 6 for oxygen, 1 2 3 4 5 6 1 2 3 4 5 6 for nitrogen. So that extra negative charge is placed on nitrogen this time, and 1 2 3 4 5 6 for oxygen. Clear? Is this diagram clear to you? But in this case, the octet is not complete in nitrogen. So for that reason, now what we do is we keep that extra electron on oxygen rather than nitrogen. Okay. See this structure here. 1 2 3 4 5 6 plus 1 electron is also there. So that is the reason it is making a bond, because electron must be here. So that extra electron is now placed on oxygen. So that will result in 2 possible structures. These both are same. Now we'll talk about this. Okay, we will talk about why these 2 structures. So although they are same oxygen, but still there are 2 possibilities, right? So if you just bring an isotope in place of this oxygen, then things would have been more different, right? Wouldn't it? Okay. So we have to restore the multiple bonding between nitrogen and one of the oxygen. In this case, a double bond. Okay, the same thing is written. To complete the octet, we need a double bond. Now, what is the difficulty with this Lewis dot structure? So first of all, it does not give the actual structure. It does give you the electronic distribution, but there is no definition of the structure, that how the structure will look like. Okay. So in case of polyatomic ions, the net charge is possessed by the ion as a whole and not by a particular atom. Here we are defining the electron is going to one oxygen or one nitrogen, but in reality it is present all over the compound. Okay. Now the formal charge on an atom in a polyatomic ion may be defined as the difference between the number of valence electron of that atom. Now we'll talk about formal charge, right? So just move to the formal charge. So this is the formula for formal charge. It is valence electron. Okay, the total number of valence electron in the atom. Total number of non-bonding electrons means the lone pair. Okay, so first of all in the free atom, then minus total number of non-bonding electrons minus half of the bonding electrons. So this gives you the formal charge. Very simple formula is this. Okay, so first of all you take a single atom, count the number of valence electrons. Now take the Lewis dot structure that you have drawn. Now count the number of lone pair and what is the number of bond pair that is present. Okay, what are the electrons that are present as bonded in case of that atom. Count those and divide by 2. Now put it in this formula and you will get your formal charge. Very easy to do. Suppose we have taken ozone here. So it is called ozone O3. We know the structure. One will carry positive charge, one will carry negative charge. But suppose we take the case that we don't know. Okay, we take the case that we don't know. So we have to calculate the charge on each of this. So how we'll calculate? We will take the formal charge formula and calculate it for each and every oxygen. 3 oxygens are there, we calculate for each. First 6 electrons, it is common for all of the 3 because valence electron is 6, so it is 6. Okay. Now, what is the number of say your this thing? It is total number of non-bonding electrons. So for oxygen 1, it is 2. For oxygen 2, it is 4. For oxygen 3, it is 6. So 2, 4, and 6. Okay. Now next is what is the number of bonded pair? For this, if you count, there are 3 bonds for oxygen. So 3 bond pair electrons. So 3 divided by 2. Okay, so 3 divided, sorry, yeah, 6 electrons are there, na? Because 3 bonds are formed. That means that 6 electrons are there because one bond constitutes of 2 electrons. So 6 divided by 2. So that will give you a formal charge of +1. For oxygen number 2, if you count it, so 2 bonds are there. So 4 electrons in total. So 4 divided by 2, that will give you 0. If you talk about oxygen number 3, it has one bond. Therefore, 2 electrons. Okay, 2 electrons. So that will give you -1. So we have seen this structure of ozone, same structure. That one of the oxygen will carry positive charge, one of the oxygen will carry negative charge, and one of the oxygen will carry no charge. So that is depicted here with the help of formal charge. Clear? So if you got this charge, then we can write it in this way. Okay, oxygen positive, oxygen negative, and oxygen. So this is your ozone molecule representation. Now, formal charge does not include real charge. So this should be kept in your mind that it is not the real charge separation within the molecule. They only keep the track of valence electron. That which valence electron is choosing the lowest energy structure because sorry, which valence electron is shared more. Okay, means C. It is shared, right? It is shared. But where it is shared more, where it is shifted more, that is the thing that is being counted by your formal charge thing. Okay. So this is just a way to represent it. So it is similar to the oxidation state that you will study that okay, it does not have a +1 or +-1 charge, is not ion, but we consider it is. Okay, so that to get an idea of polarity also, right? So in this way, we get the lowest energy structure because now we know that this charge is here, this charge is distributed more over here, so we get the lowest energy structure. The formal charge are based on pure covalent way of bonding, assuming electron pair are shared equally by the neighboring atom. Now, limitations of octet rule. Again, why this octet rule failed? First of all, structure is not defined. Okay, we told although it is called Lewis dot structure, but where is the spatial arrangement, right? Second is there are many exceptions to this octet rule, and when you will go to higher and higher elements, your octet rule will be ruined. Okay, it will be beaten to the bits of paper, right? Because we don't follow an octet rule when we go to higher elements. It's getting 16 electrons. Someone is taking 32 electrons. So nobody cares when we go to higher electrons. So we'll see that. Okay, but for lower atom, still it is applicable, lighter atom. But as we go higher and higher, this does not count anymore. So there's really 3 exceptions to this. Say our octet rule. So first we are talking about the limitations of octet rule. In some compound, the number of electrons surrounding the central atom is less than 8. So here are 3 examples of those. LiCl. Okay, it is less than 8. BeH2 less than 8. BCl2, BCl3 again less than 8. How it is less than 8? I am saying that less than 8. So boron has 3 electrons, right? Okay, boron has 3 electrons, and here it is sharing that one electron to each of these Cl. Now, what are the total number of electrons on boron? Just count it: 1, 2, 3, 4, 5, 6. Incomplete octet, right? We talk about beryllium, hydrogen, helium, lithium, beryllium. 2 electrons are there. So it can donate 2 electrons and gain same at the same time 2 electrons more. So 4 electrons are there on beryllium. Again, the octet is not complete. For lithium also, the octet is not complete. So this all compounds in which the octet is not complete or the number of electrons is not equals to 8, they are called as hypovalent. Okay, hypovalent. So hypo means less. Okay, hypo means less. So they are all hypovalent. Next is odd electron molecule. So I have stated earlier that atoms avoid to have a single electron rather than a pair of electrons. But there are exceptions to it. So if we talk about the exceptions, then I have the example of nitric oxide. So it has N and O present here. If you just see here that nitrogen has 3 electrons. Okay, so one pair of electron is this and one single electron is here. So it is defying that rule. Okay, it is defying that rule. Similarly, here also nitrogen dioxide, if you see here, so nitrogen has 1 electron here. Okay, it is not having a pair. So here also this odd electron molecules are seen. So this is very confusing for students. How you will draw the Lewis dot structure? So you should remember this, that in some cases we have odd electrons. Next is expanded octet or hypervalent compound. Okay, so this will ruin this all this octet and all. You just see this complexes. Phosphorus, sulfur means the compounds of phosphorus and sulfur. Just count the number of electrons here. So it is making 5 bonds. So that is giving you 10 electrons in the first state. Because each bond has 2 electrons. So 5 bonds of 10 electrons. Although the surrounding atoms are completing their octet, but the central atom is going beyond the scope. The reason is, if I talk about the reason, the clear reason is the involvement of d orbital, because they are above the third period, right? Now third period are capable of having d orbital, and that is ruining the octet rule, because they can say they can accommodate more and more electrons now due to the availability of d orbital. Okay, clear? Next is SF6. Again, it has 6 bonds. Okay, 6 bonds means it is having 12 electrons. Again, this octet rule is just look at this H2SO4. It has 6 bonds again, so it has again 12 electrons. All of its electrons are involved in bonding, that is resulting in hypervalent compound. So the one with the less number of electrons than the octet are called hypovalent. The one with the more number of electrons than the octet, that is the 8, it is called as hyper. And the third exception is your odd electron rule, whose two examples are NO, that is nitric oxide, and nitrogen dioxide. Now, other back drawbacks for the octet theory, as I have told you, shape of molecules is not defined. Okay, first this, it does not explain the relative stability of molecule, being silent about the energy of molecules. They are not talking about energy, so there is no description for that. Okay, and third is, what about the bond formation? Why is the inner core electron not involved? So there are repulsions from the inner core electrons also, but we are not getting, or we are not including those. So what about those? So these are some exceptions to the octet theory. Now for that, we have our next theory, that is valence bond theory. So we'll study that in the next class. So for this, we have completed our Kossel-Lewis approach. Thank you.